Okay, here's the calculator portion of the exam. This first problem is obviously a calculator problem because we've got all these digital decimal type choices. We also have a function that's rather involved. We have a quadratic times a log function that says acceleration is the derivative of velocity. That would normally not be there. I just wrote that there to remind you how to do this. A particle moves along an x-axis. This is in a straight line, so that any time the velocity is given by, what is the acceleration? So all we have to do is we have to find the derivative of this function evaluated at 6. And there's a very nice app that does that. On the calculator, we could enter in this function, t squared log of t plus 2. And if I want, I could actually use alpha t. There's no need to do this, but I'll do it here in this example. T squared log of t plus 2, alpha t plus 2. And then what we're looking for, the graph is not useful. I mean, here's the graph in the standard window. We don't see a heck of a lot. It seems to be right next to the x-axis there, or the t-axis. So let's not go there, but rather just go math 8, which gives us our numerical derivative. I'm in classic mode here. This is the mode I prefer. You might want to try the pretty print or the math print mode. We need 3 inputs. We need the function, which we called y1. We need the variable, which we called t. And then we need a particular value at which to find the derivative, and that would be at 6. So we dump all those guys in there. We get the answer 29.453. Okay, so that's the answer. Of course, when you're doing this, you could have gone, let me clear that off. You could have gone directly math 8. You could have dumped in the function as given. I'll use x this time. The variable that we use is really irrelevant because we're going to say the variable is x, and then we're going to put in 6, right? So we get exactly the same answer a lot more quickly. If we didn't have a calculator and we needed to try to do this by hand, we could get v prime using the product rule, right? The derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. The derivative of log of t plus 2 is 1 over t plus 2. And then we're supposed to evaluate this at 6. So that would be 12 times the log of 8 plus 36 times 1 over, we're putting 6 in 1/8. So the question is, well, I don't have a calculator box. Okay, how am I supposed to do the log of 8? We know something about the log curve. It looks like this. It goes through this point 1, 0. It goes through another point E1. It goes through another point over here, E squared, comma 2, right? So these are points on the curve. E squared is really close to 8. So if we, I mean, E is about 2.7. E squared, if we just jumped on our calculator here for a minute, E squared is 7.3. Okay, so let's say E squared is about 8. So the log of 8 would be about 2. So this product here is about 6. And then 1/8 of 36. Well, if we had 1/6 of 36, that would be 6. 6 plus 6 is 12. Well, that's not going to quite give it to us. Well, we do have the answer here, 29.435. I'm thinking we probably could have estimated this. Oh, I can't multiply dummy Joe. 12 times 2 is 24. So 24 plus 6 is about 30. Yeah, there's the answer. That's the only one that's reasonably close. So conceivably, you could have done this without a calculator, but with a calculator, it's a 10-second problem. 77. This is obviously not a calculator problem. There's really no numbers in here, no functions. Only about 40% of the calculated permitted problems actually require a calculator. I gave you 10 on this exam. You're going to figure about 5 will need a calculator. The other 5, a calculator doesn't do you any good, and this is an example of where the calculator doesn't do you any good. So we've got h is some differentiable function, which means we can find a derivative. The temperature in degrees Celsius at a weather station for T hours. So you can imagine there's a T graph, and this is temperature in degrees Celsius, and this is h, right? H is the function, gives the temperature in degrees Celsius. And T is ticking off in hours, 0, 1, 2, 3, and so forth. What is the best interpretation of h prime? Well, first of all, you know that h prime gives a rate of change. It's the slope of the tangent line, rate of change at any hour at time, whatever the time is. This is h prime of 24, so h prime of 24 would give the rate of change at time 24. So you're going to think, you know, as you're ticking along here, here's 1 hour, here's 2 hours, here's 3 hours, here's 24 hours out there, and there's some curve, and we're looking for the slope of the tangent line. M would be h prime of 24. So once you have the idea that you just go down, you know, the change, no, we're looking for a rate of change here, rate of change. This says during the first day. We don't want that. We want at the end of the 24th hour. That's the one we want, right? So at t is equal to 24. 78. The derivative is the instantaneous rate of change of a function. Duh. Again, that would not be given. I just put that in there to help you think about how to do this. The first derivative of a function f is given. Was the instantaneous rate of change of f prime. So we're looking for f double prime at 2. That's what we need. But we already got f prime. F prime is given as x minus 4 e to the minus sine of 2x power. And we're looking for the second derivative at 2. Again, we could just jump straight into the calculator, math 8. We put in the function that we're trying to find the derivative of. That's x minus 4 e. I'll use my e to the caret button over here. Negative sine of 2x. And again, because I'm using 2x, Joe, 2x, because I'm using a trig function here, I better make sure that I'm in radian mode. Let me just double check. Yeah, I am. That's the default. Anytime you deal with trig in calculus, make sure you're in radian mode unless the problem explicitly says degrees. Okay, so that's the function. The variable that I used was x, and the number I'm trying to find is 2. The rate of change there. So the answer is negative 10, and I'm done. So playing the devil's advocate just for a minute, suppose I didn't have a calculator. Could I come up with that answer? Well, let's do just a real quick and just see. What is f prime of x? F prime of x is here, f double prime. Okay, so the derivative of x is 1 minus 4. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Well, the derivative of a minus sign is a minus cosine of 2x times 2. So it looks like we got 1 minus the 2 can come out here with the 4, give me 8. E to the sine of 2x, sorry, minus sine of 2x times a, oh, we have a minus sign there, so that's plus cosine of 2x. Okay, so there's the derivative. And if I want to get the derivative evaluated at 2, the exact answer would be 1 plus 8 e to the negative sine of 4 times the cosine of 4. And that's the exact answer. Okay, so I mean, conceivably, this could have been a non-calculator problem. And just to make sure I'm not blowing smoke here, 1 plus 8 times e raised to the negative sine of 4 radians, right, times the cosine of 4 radians. And that should give us that exact same decimal, which it doesn't because I have that. So close the exponent. and then times cosine. Okay, so negative 10.1456. That's the exact answer, but I don't have a calculator, Ms. Bosquet. How am I supposed to get that without a calculator? Well, let's just do a couple of approximations here. We know that the sign is always between plus and minus 1, about plus or minus, right? The sign of anything, the sign of a function is between plus and minus 1. Now let's just take the average. We'll call that 0. And then the cosine is, again, between plus and minus 1. Here's a cosine wave. So cosine wave is between plus and minus 1. Again, I don't particularly want to call that 0 because that might be a little misleading. Let's see. Where is 4? Maybe we can do both of these. Where is 4 radians? I don't know where 4 radians is, Bosquet. Well, let's see. There's pi radians, right? That's 3.1. Here's 3 halves pi. So that's about, what, 4.5. So 4 radians is somewhere down here. And we could say that the cosine would be about negative 1/4. And the sine of 4 radians is, I don't know, negative 0.8 maybe. So this is e to the 0.8 power. Is that going to help me at all? We're supposed to come up with a negative 10. Let's see, we've got 1 plus, here's the negative 1/4 times 8, so that's negative 2. And then we're going to have e to the negative 0.8 power. Certainly this is going to be a negative number. So, I mean, if we had to guess, I suppose we could throw these out. Why could we get negative 10? I don't know. This is 1 minus 2 over e to the 0.8. I don't see it easily. So I hope you have your calculator. Easy problem with the calculator. Here's a problem where there's, again, no numbers. Calculator doesn't do us any good here. F is a continuous function on a closed interval. What must be true? So one of the things you might want to do is just imagine all the possible continuous functions on a closed interval. So we have a closed interval from A to B, and we're just drawing various continuous functions. So maybe it goes like that. Maybe it goes like that. You know, maybe it has some sort of whifferdale in there where it goes up and then down. There's an infinite number of continuous functions. Let's see. There is a number c such that f of c has to be 0. Well, none of these functions have 0 as the y-coordinate, so that's out. We don't have to do that. We could, right? I mean, we could have had a function that had a 0, right? If this is a and this is b, we could have done that, but we don't have to. There's a number c in the interval such that f of a, the left endpoint is the smallest, and then c is in the middle somewhere, and then the right endpoint is the largest. Well, that would be true for this green one, but it's certainly not true for the red one. The red one, the left endpoint is the largest, and so that's out. There's a number c in the closed interval such that f of c is bigger than anything else in the function. So is there a absolute max? Well, this is called the extreme value theorem, and this in fact is the right answer. No matter what function you draw, there's always going to be a high point. For this green one, it's the right endpoint. For the red one, Lmax there at the beginning. They always have a point that is larger than or equal to everything else in the interval. That is the true statement. F prime has to be 0. No, that's wrong. Look at the red one or the green one. There is no spot. There's a number c in the interval such that this is the mean value theorem. And it would be true if the function were differentiable. For all differentiable functions, if you look at the slope of the secant line, there is a point C in here somewhere where the slope of the tangent line is the same. That's what this says, slope of tangent line, slope of secant line, mean value theorem. But that's only if the function is differentiable. We could still draw a continuous function, for example, that has a cusp in it or a corner. And here, the slope of the secant line is that, and there is no spot where the tangent line is the same. So that is false. If the original problem said was differentiable, then that would also be true. Both C and E would be true. But right now, the only answer that's true is C. Number 80. This is a limit problem. The numbers look pretty simple. We could do this on our calculator, I suppose. If I just go into y equals and dump this function in, e to the 3x, e to the 3x, take away 1. Remember, you probably did this in pre-calculus, divided by the sine of 5x. I guess I didn't need a pair in there. That's a function. Here's the graph. If we want to look at a graph, whoa, it looks crazy. But the question is, what happens when we get close to 1? So if we trace and we put 1 in there, or sorry, close to 0, we find the function's undefined, right, because you get 0 over 0. But if we put in a number close to 0, like 0.00001, that's pretty close to 0, we get about 0.6. On the other side, negative 0.00001, that's also close to 0, and we get 0.59999. So the answer is 3/5. If you didn't want to do it on the calculator, you could have just used L'Hopital. Okay, so L'Hopital says, look at this limit as x goes to 0. The derivative of the bottom is 5 cosine of 5x, and the derivative of the top is e to the 3x. Evaluate 0 in there, we get 3 e to the 0, and 5 times the cosine of 0, and so that's 3 over 5, right? The cosine of 0 is equal to 1. 3/5. 81, obviously a calculator problem here because of the numbers. We might be able to think about it and come up with an answer without a calculator, but let's see what's going on. A definite integral provides the method of finding the product of two quantities when one factor varies. That would not be given, but that is true. This has a tank, has a bunch of water in it. The next 6 minutes, water flows out at this strange rate. This is a rate of so many gallons per minute. So how many gallons are in the tank at the end of 6 minutes? Let's go to a middle school problem. Let's suppose we had 81.637 gallons originally, and water flowed out at a rate that was constant. Suppose it came out at 10 gallons per minute. So I just kept it the same. And the question was, how much would be in there at the end of 6 minutes? Well, let's see, 10 gallons a minute times 6 minutes, we would have lost 60 gallons, right? So the answer would be 21.637. That's if the rate coming out is a constant. Easy. By the by, I would hope that you could throw this out right off the bat. If you start with 81 gallons, you can't have 126 gallons when some goes out. So we know it's not choice C. What is the correct answer? So the definite integral does allow us to calculate that amount going out. So let's see. The integral from 0 to 6 of this rate now, 9 times the sine of the square root of t plus 1 gallons dt. Okay, so let's think about what's going on here. The units here are in gallons per minute. Gallons per minute. The t are little tiny pieces of minutes. So sure enough, when you multiply these together, the minutes cancel, and this gives us gallons. Okay, so that definite integral will give us gallons. Let's go ahead and we'll just go straight to our, now to do a definite integral, it's math 9. So we put in the function that we're trying to integrate, 9 times the sine of the square root of t plus 1, I'll use x. Right, it's a dummy variable, closes the radical, closes the sine, comma, the variable is x, comma, lower bound, comma, upper bound. Okay, so 45 gallons flow out. We had 81 in there to begin with. So 81 0.637, and we take away that answer, and we get 36 gallons. Okay, so that's how much is in the tank. Could you guesstimate that without a calculator? Well, I don't know. That would be interesting to try. Good thing we have a calculator. 82, table above gives values of f, f prime, g, g prime. The function h is given as a product, and we need to find the derivative of h. So that screams product rule. So h prime of x is going to be the derivative of the first times the second plus the first times the derivative of the second. That's straightforward product rule. So h prime of 1 is f prime of 1. You probably did a problem very similar to this when you did product rule stuff. It's in every calculus textbook. I'm sure I could find it in yours somewhere. So then we just go to the table and we chuck in the numbers. F prime of 1 is -3. G of 1, according to the table, is -1. F of 1 is 3. And G prime of 1 is 2. So we'll get 3 plus 6 is 9. There's the answer. 83. Definite integral problem again. Well, I'm just going to jump straight on to here. Math 9. Dump in the function. This is sort of nasty. I tell you what, I'm going to put the function in here so I can see it a little bit more clearly. E to the tangent of x power, close off the exponent, and then divide that by the cosine squared. So cosine squared. And hopefully you know how that syntax works on the calculator. Okay, so my function I just called y1. The variable I'm using is x. Lower bound is 0, and upper bound is pi by 4. Bang. 1.71. That's not one of my choices. But I do note, I know E is about 2.7 1828, right? So E minus 1 would be 1.7 1828. And sure enough, that's what my calculator says. So the answer is choice C, E minus 1. Now, suppose we didn't have a calculator. Could we have gotten that without a calculator? And the answer is yeah. We know the integral of e to the u du is, in fact, e to the u. And here my u is the tangent of x. The derivative of tangent is secant squared of x dx, which we could write as 1 over cosine squared. Right? And sure enough, that's what we have. So this simply works out to be e to the tangent of x and evaluate between 0 and pi by 4. So fundamental theorem, I use the upper bound first. I get e to the tangent of pi over 4. Take away e to the tangent of 0. And you should know some basic facts about the unit circle. And so pi over 4 is right here, and the tangent, remember the ordered pair is root 2 over 2, root 2 over 2. Tangent's y over x, so this is e to the 1. And the tangent of 0, an ordered pair is 1, 0, y over x is 0, e to the 0. So e minus 1. Choice C. No calculator needed. 84, this one screams calculator. The average value of function on an interval is defined as the rate at which water is sprayed on to a field of vegetables is given by this function R. What is the average rate of water flow in gallons per minute? Okay, so again, we're just finding, just use the problem as given. 1 over B minus A. So here's our average. Average rate is going to be 1 over 4 minus 0 times the integral from 0 to 4 of the rate. If we just consider units, this is in gallons per minute. This is in minutes. Gallons per minute times minutes gives us gallons. But then this is minutes, right? So this is 1 over minutes. And our final unit is going to be gallons per minute, which is what we want. So it looks like we just do 1/4 times math 9. We're integrating this funky little function to radical 1 plus 5t cubed, 1 plus 5, I'll use x cubed, close the radical. Comma, variable is x, comma, 0, comma, 4. 14.691, choice C. 85, a left Riemann sum or right Riemann sum, a trapezoidal sum are used to approximate the value, each using the same number of subintervals. Doesn't say how many subintervals, maybe we just do 2 or 3. The graph of the function is increasing concave down, which gives an underestimate. So if we did 3 subintervals, okay, and we drew boxes from the right side, this would be our right Riemann sum, all these boxes coming from the right side. Well, that's an overestimate. So a right sum overestimates. How about a left sum? Again, we're going to use 3 boxes. They're all the same. And we do a left sum. So now we're coming in this way, and this way. Well, that's a severe underestimate. This first box has height 0. So left sum is under. So that's good. We want underestimates. And then trapezoids. So a trapezoid, let's see, we'll use 3 trapezoids in here. So a trapezoid, we're just connecting these like this, right? And that goes there, it connects, and that goes there. And again, just by the fact that the curve is concave down, when you draw a trapezoid, that's going to underestimate it. So that's also an underestimation. So the answer is 1 and 3. 1 and 3, only choice D. Okay, that's it. That should have taken you about a half an hour. Let's stop this here.